So the next speaker is Dr. Anusha from Indian Institute of Astrophysics. She works on radiative transfer. And so this is sort of slight shift of gears. Yesterday we were doing hydro. Today you heard a little bit about MHD. Now we are talking about a slightly different topic, which is interaction of matter with photons. Okay, so that's what she's about. So Anusha, over to you.
Thank you. Good afternoon, everyone. So I'm Anusha, and as he already mentioned, I'm from the Indian Institute of Astrophysics. So you have by now have a fair idea of hydrodynamical equations, magnetohydrodynamic equations, and why they are important. For example, you know that they are important to describe the physical quantities such as energy, density, momentum, magnetic fields, and so on of an astrophysical plasma. We are basically focusing on astrophysics here, so I'll be referring to astrophysical environments mostly in my talk. So similarly, we need solution of radiative transfer equation, the so-called radiative transfer equation, which I come to that later, the proper form of it and all. And the solution to this is necessary to describe the radiation field. For example, this is important to understand how this radiation field affects the parameters such as temperature, pressure, energy distribution in an astrophysical environment. And also, by modeling the atomic and molecular spectra, we can infer the gas composition of that particular environment, for which we need the solution of radiative transfer equation. So in first 1 or 2 slides, I will describe you a few of the terminologies or a few concepts that I will be using throughout my presentation so that you don't feel out of space. So one of these is the local thermodynamic equilibrium, or LT. LT is an approximation when the spacious case over which the temperature changes are much larger than the mean free path of the particles. And also when the scattering of radiation on atoms can be ignored or can be insignificant. When it is insignificant, we can assume that locally there is thermodynamic equilibrium. And in this case, the source of the radiation can be assumed to be light. That means you are assuming that the source is just emitting like a blackboard. And in this situation, we say this is in local thermodynamic equilibrium. And in general, the solution of radiative transfer equation is quite complicated. But however, if you have this approximation valid in that particular environment, then the solution becomes trivial. It is just one-step solution. And for example, when there is high density regions where the thermal motion is dominant, for example, in a solar photosphere, you can have this approximation to be valid. And then the transfer equation is not a big deal. However, when you go to a low density layer where the scattering of radiation and atoms becomes important, you cannot assume this. And in that case, the transfer is a radiative transfer equation. So I'll be using this terminology so that you don't get confused. I'm clearing that out. So the transfer equation becomes non-trivial and it becomes extremely non-linear. And this is known as non-LTE radiative transfer equation. Now I will also describe few of the radiative and collisional processes that become important. There's a question. Yeah. Yeah, that is basically when you assume LTE, then the luminosity will be different. Which will the matter is completely emitting like a block body, and then it depends on temperature, and then the luminosity will be sigma t to the power 4. So that is in context of the when there is such thermodynamic equilibrium. So yeah, and so yeah. Now let's go to some of these processes. You can see here the cartoons. I have divided this into radiative processes and collisional processes. Now, what's this is energy levels of an atom. For example, n equal to 1 corresponds to ground state, n equal to 2 to the first excited state, and so on. And then there is this free state or the continuum state. And suppose that there is a photon with energy h nu that is incident on the atom, takes the electron to the first excited state, and this process is called as radiative absorption. So I would like to stress these processes here because I will be using these in the coming slides. So this is a radiative absorption that takes the energy from the photon, electron to the excited state. Similarly, there can be radiative emission or radiative de-excitation. That is where, suppose that the atom is already having already in the excited, the electron is already in the excited state, either due to radiative or any other process like collisional, which I'll come to that later. So suppose that, and then it just de-excites to the ground state through emission of a photon with energy h. This is known as radiative emission or radiative de-excitation. Then there are stimulated emissions where a already excited atom gets incidence from a photon with energy h nu, and then while de-exciting, it will emit two photons. Similarly, a photon can be incident on the atom so that it takes the electron into a free state. That means it will separate the ion from the electron, which makes the atom ionized. So this is known as the radiative ionization or photoionization. And there can be the reverse process, radiative recombination, and similarly there can be stimulated recombination, which is the combination of proton and electron which come together to emit a photon and to make the neutral, in this case the hydrogen. These are some of the radiative processes that become important in doing radiative transfer equation. Similarly, there can be collisional processes. You can see that there is an electron that collides with the atom, takes the electron to the excited state. This is known as a collisional excitation. Similarly, there can be collisional de-excitation where an electron hits atom, takes the energy of the electron which is in the excited state. The electron comes to the ground state without emitting any photon. So that means whatever is the energy of the electron in the excited state is taken away by the collisional. That's taken away by the kinetic energy of the. It is converted into kinetic energy of this electron. So you can have, for example, combination of radiative absorption. A photon is absorbed by the electron, goes to the excited state, but then it is collided by an external collider, takes away the energy, and it comes back without de-exciting. So this process, for example, is important in formation of spectral lines. For example, an absorption line is formed in such a sequence. Similarly, there are collisional ionization. Collision makes the atom go to the free state, and then there can be collisional recombination, and so on. So
in this stimulated recombination, so the energy of emitted photons are less than this. The sum of two photons is equal to h nu or what?
So the kinetic energy of these two and this energy, these are the total energy that is divided into the energy of these two photons. So one photon is same as the one that comes together, and another is the kinetic energy of this that gets converted into the photon.
But isn't it sort of violating the conservation of it? Because the rest mass energy of hydrogen is as if like mass of proton plus electron, and you have photons in the radiative state, one photon on the left hand side. So they're different.
I don't know what is violating here. So
It's not same. Different.
Yeah, that's
Yeah.
So this kinetic energy is okay. You are getting confused because you are thinking the new is okay. Okay. So sorry. This is the totally this one h nu corresponds to the energy of the colliding particles, and another new h nu corresponds to this. I mean, this is just for illustration. So I will change it for a new prime or something in the next lecture. Yeah. So yeah. So then we can go to next. Yeah. So I think you all know what are spectral lines. So absorption and emission lines. I just want you to recall that the absorption, emission, and scattering of radiation of atoms, the scattering of radiation by atoms and molecules, it leads to the formation of spectral lines, which can be observed from Earth. I'm specifically referring to the spectral lines formed in astrophysical environment. But modeling the spectral lines is vital proof for understanding the composition of the astrophysical crystal. And yeah, as you already know, I don't have to go into the detail of how an absorption or an emission line is formed. Now you can see it is just an old example, but you can see that this is the form of emission lines here, which show as peaks, and then these tips are absorption lines.
This is from the sun.
Yeah, this is from the sun, but it's an old example. I was trying to find something. I thought this covers everything, so this it's like a good example. Yeah. And numerous physical problems require a detailed understanding of the radiative transfer equation solutions. And this can be in a stellar atmosphere, planetary atmosphere, interstellar medium, and intergalactic medium. So now I start with our favorite closest star, that is our sun. This image here shows different layers of the sun. You can see this solar photosphere here, these dynamic events which are flares, this chromosphere, corona, and so on. And in this plot, the temperature and density as a function of height in the solar atmosphere. This is the base of the photosphere and goes up to 3,000 above kilometers. Temperature and density are plotted here. So the solar atmosphere itself can be considered as a laboratory because density varies nearly 12 orders of magnitude and temperature range from thousands of kelvins in the temperature minima region, for example, where chemistry can become important, to millions of Kelvin where plasma is fully ionized. Now, the entire atmosphere is also dynamic on timescales from seconds to months. And in particular, chromosphere is a very interesting layer because the chromosphere heating to millions of Kelvin, chromosphere and corona, the heating of the atmosphere to millions of Kelvin, needs to be understood. And for this, we need the understanding of the radiation field, how the energy is transferred from the photosphere to the corona. To understand this, the radiative transfer equation is important. So, for example, this flare here can be seen as a dynamic event, and such dynamic events that happen in the chromosphere, to understand these, whether these dynamic events are responsible for the solar chromospheric heating. Yes?
In previous slide, you said that there are unsolved problems in chromosphere, not including the fundamental like what exactly.
I'll come to that later, maybe in the later slides. It is shown actually, so you will come to know that what are these fundamental physics. That so just to summarize, the radiation, the treatment of the radiation field, that itself is not treated properly because it's a very complex problem and computationally extremely expensive. So people tend to make a lot of approximations. They just assume LT in chromosphere, for example, but that is not the case. So the scattering is important, and this can lead to discrepancies. So you cannot really, you have this always high resolution and highly advanced instruments which can observe the spectral lines in these dynamic events. But when you actually want to model them, forward modeling, you cannot really reproduce because you are not taking into account the proper physics behind it. So yeah, so to understand the role of radiation field in the chromospheric heating, also we need the radiative transfer solutions. And the best way to answer all these questions is to numerically model. We will call the theoretically or numerically model this chromospheric layer. Now let's little bit move to the planetary atmosphere. So basically, I work in sun and stellar atmospheres. So all the different examples I show in the next slides are just for illustration purposes. So if you have more doubts, I can give you some references here and you can go to the details. So as you know, the planetary atmospheres are much cooler. Therefore, the composition is mostly in terms of molecules, and they are not source of radiation. So therefore, they basically, the surface reflects the stellar radiation that is near to them. And because the composition of molecules, they are able to scatter, absorb, and also there is reflection from the surface of this planetary atmospheres, and it also forms molecular spectra, which can be observed from Earth. And to give you an example, if the atmosphere is carbon dioxide rich, then the collisional rates, the collisional processes that I described you in a slide, that becomes more dominant, and this leads to the approximation of LTV to be valid in a particular and up to densities which can be much lower. So in this case, the problem becomes much more simpler because one can assume LTV. This happens, for example, in the atmospheres of Mars and Venus. For example, in these planetary atmospheres of Jupiter, Saturn, etc., the non-LTE starts to become important because methane, because of the presence of methane in the mesosphere, the non-LTE, which is a complex form of the radiative transfer equation, has to be solved. So this is just a picture which shows different components of the planetary atmosphere radiative transfer. The reflection by the surface, aerosol scattering, the reflected solar radiation. This is the incoming. This is particularly planets in the solar atmosphere, but it is, generally components one has to take. So emitted by the atmosphere and so on. Now let's go a little bit further to the interstellar heat. So as you may already know, dust is everywhere. It is in planetary atmospheres, it is in interplanetary atmospheres or interplanetary medium, interstellar medium, or even in intergalactic medium, dust is everywhere. And these dust grains, which are made up of all these things, they're efficient in absorbing and scattering. And because eventually it's mostly like an absorption and scattering and all these processes, you have to take into account the opacities of this dust when you do the radiative transfer solutions in an interstellar medium in particular. So if you want to understand the intrinsic quantities of the interstellar medium, you have to take into account the presence of dust grains, and which are efficient in absorbing and scattering the radiation, which could be from the source, which is a stellar emission or any other emission sources. So this is just an image that can show a star formation region. This is a bright region. This is a reference here. Yeah. Now we go to cosmology. Again, I'm not an expert in cosmology, and I'll give you some illustrative examples. So this is just an illustration of the so-called Lyman alpha forest. So what is here is a source that is emitting radiation. It could be a quasar, and the radiation is passing through the intergalactic medium through all these clouds. These clouds are basically made up of hydrogen. So the continuous line here, this is from the source, that is emission from the source. And on top of it, you see all these dips. These are the lines from the Lyman alpha transitions, Lyman alpha line, which is from the hydrogen neutral hydrogen that absorbs the radiation from the source. And because all these clouds are different redshifts, this is continuously being shifted towards the longer wavelength region. So this is an example to show that. So you have like forest. This is called Lyman alpha forest. This is the forest of Lyman alpha lines. Although all those are supposed to be at 1 to 1.6 angstroms, if it was observed without any far away, which it was here. But then because of the redshift, they are all continuously shifted. And to analyze this, you have to use radiative transfer equation because, with your hydrogen as an atom in your gas, you have to solve radiative transfer equation with the main component of your gas being hydrogen. And that was an illustrative example, but here it is a real observation. So all this dark region here is a highly dense Lyman alpha lines, spectral lines. And then there is this reionization of the intergalactic medium, where there is energetic UV radiation from the very first stars that are capable of ionizing the local bubbles of hydrogen. And to understand a detailed modeling of the spatial correlations between the source and sinks of this ionizing radiation also requires radiative transfer simulations. Okay, for now I have given a broad examples of different applications of the, there are still more. There is supernova ejecta, atmospheric supernova, where also the radiative transfer is important. I have given you a few examples. Now let's come to the technical part. So this is a set of hydrodynamical equations. You would have already seen this. So this is a continuity equations, momentum, and energy equations equation. So you can see here, this is a pressure term, and this is a Q rad. This is a new term which is corresponding to the energy for the this is in the energy equation. This is basically, I'll come to that what it is. But these are the two terms that are coming from the solution of radiative transfer equation. You can do any approximation, but eventually these two components should come from the radiative transfer pattern. So this is a inclusion of magnetic fields. This is how the hydrodynamical equation are changed to magnetohydrodynamical equations. Additional heating term in the energy equation, and eventually you have this Q rad. So assume that you have a gas in which you have n levels of hydrogen. We consider hydrogen to be in n levels. And suppose that also you consider few molecules, H plus, H2, H2 plus, H minus, and assume that there are a number of other elements, calcium, magnesium, etc. And the solution of radiative transfer equation eventually gives you N, which is the number density of these atoms at different excited and ionized state, that bounded at free state. And also it will give you the radiation field, the intensity angle, which is denoted as I, which is the intensity of the radiation field. These are the two outcomes, the first outcomes from the solution of the radiative transfer equation. Now I told you the pressure is an input to the hydrodynamical equation. And how do you compute the pressure from this composition? The solution gives you N in different subscript I corresponds to different elements and different excited and ionized states. So eventually this NEKT, N is the electron density, and this is the Ni are the different elements. And adding all this will give you, adding these partial pressures will give you a total pressure. You can give to the emission model. Similarly, I mean, then this itself depends on temperature. How do you compute temperature? How do you determine temperature? When you do exact calculations, the total energy, when you solve energy equations, you will have total energy, and that should be conserved. So you divide it into kinetic and the internal energies. Therefore, all these internal energies in the excited and ionized state of all these elements in different states, due to ionization and excitation processes, that has to be taken into account here. And then you have the kinetic energy, which contains total N here. This N is a total N containing the composite, the sum of all the elements. And then by dividing the total energy into kinetic and internal energy, you can basically determine energy. So this is a nonlinear process. You solve the collisional and radiative processes together, which is called as a rate system, solving the rate system. So radiative transfer equations, so solving rate system gives you N, solving transfer equation gives you I, and then you can compute the temperature by energy balance, and then compute the pressure, and the Q that was in the energy equation, which is called as the flux divergence, which is basically the divergence of the flux, where flux is flux of the radiation is computed using this interval. This is the I, which is the solution of the transfer equation, giving you the specific intensity from the transfer equation solution. So basically, you give this flux divergence, Q, and the pressure to your hydrodynamical quantity. So the physical meaning is that when Q is positive, it means that it is a source of heating, and when Q is negative, it means that it is a source of cooling. So if you want to include the continuum cooling or light cooling, or how the heating and cooling processes are coupled with the hydrodynamical equations in order to evolve your energy, and how the temperature finally evolve, for that you have to include this too. And all the complex radiative transfer solution that you have doing gives you just these two numbers eventually. Okay, sorry about that. So when we were converting from Keynote to the Microsoft Teams, this is a bit offset here. But yeah, anyway, this is a general form of the transfer equation. So I finally come to the mathematical form of the radiative transfer equation. And I'm not including any redshifts and everything here. This is relatively simple, although this in itself is a very nonlinear and complex form. This contains this first term, which is the time derivative of the radiation field I, and c is the speed of light. R is the position vector. Omega is the ray direction, the direction. It contains two components, polar and azimuthal angle of the ray. X is the frequency, and the cutout is the opacity. And this opacity also depends on R, omega, and X. And then you have this term, which is basically the radiation field. In 1D, it is just a d by dz. It is the derivative. Spatial. This is the spatial derivative of the intensity at position vector R, omega, X. On the right hand side, you have the source to send sinks. So S here is basically called as the source function, which is the ratio of emissivity to opacity. So let's not worry about that here. You can assume that, I can give you an example. In the approximation of local thermodynamical equilibrium, this source function is just Planck function. So once you know this form, it is just a simple, and suppose for the moment that you don't have this dIdt term, then it's a simple radiative transfer equation which can just be solved in one step. However, this term is important when, for example, you are considering the radiative transfer in a supernova atmosphere, because the travel time of the light and the characteristic flow time are here given. In that, because the flow will be maybe 10,000 kilometers per second, the velocity is that high, that you have to consider this. In a solar atmosphere, for example, this term can be safely neglected, because comparing the time scales dynamic compared to the dynamical time scales, the flow, the photon travel can be assumed to be instantaneous. So now let's forget this dIdt term, and then you have this. And this is the form which is basically used in stellar atmospheres, in particular solar atmosphere. This is the form. So now this is like a discretized atmosphere with all these points as a stratification of your atmosphere into one-dimensional height scale. And suppose that there is a ray that is passing through the atmosphere and you want to compute the radiation field at this point. Now what you do, you just solve this as a formal solution of this, which has this form. And this corresponds to the directly transported part, with I0 being the incident intensity, maybe the intensity from here to this. And then this integral here corresponds to the spatial coupling. This is what is making the problem much more complex, because there is this spatial coupling. And the source function here, I told you that this is the ratio of emissivity to opacity. And when the scattering is important, when there is no approximation of the thermodynamical equilibrium, local thermodynamical equilibrium, these both emissivity and opacity depend on the population n, and that n itself depends on I through the rate equations. And this is making the problem much more complex, because when you substitute source function in terms of opacity and emissivity, and that in terms of I, eventually you have an integral differential equation, I depending on I. You think you have solved the problems. Which problem? You have not. And this is an integral differential equation to solve which you have to use numerical methods. So you have to do iteration and so on. So maybe you assume the source function to be something simple to start with, and then you devise your numerical methods, operator splitting, etc., etc. And then iteratively it will converge to a solution which is proper solution to this equation. So radiative transfer equation in 3D space in general is a 7-dimensional problem. So you have 3 spatial and 2 angular, 1 frequency and 1 time. And you can have different geometries. It could be 1D plane, which is a simplified most simple approximation. If you want to understand general properties of a stellar atmosphere, for example, 1D spherically symmetric, it could be 2D or 3D sphere or a Cartesian 3D flow. Then there are several complex physics. You can include velocity fields in order to consider the flow of the matter, and then you can include magnetic fields and polarization if you want to understand the scattering which causes the polarization, or magnetic fields that also cause the polarization of the radiation field. And then there is line and continuum scattering, which leads to cooling, and there can be redshift cosmological applications, and then there can be non-equilibrium rate systems, and so on. The applications are multifold. Now I come to what you are asking. What Actually, we do. This is all like general description. So if you were assuming local thermodynamical equilibrium, then at a given temperature T, atoms are distributed over their Brown levels according to your Boltzmann excitation equation. And in LT, the number density of the atoms of successive ionization states is calculated in Boltzmann ionization equation. So this is a form of your LT Boltzmann equation. These are all bound levels, and then this is the ratio of the number density of atoms in excited level I, ionization state T, J to the chemical species K. So you just depend on the local temperature. And for Saha ionization, you need the electron density E and the temperature T. So if these two quantities are given, and then you need all these partition functions, the ratio of two successive ionization number density of the elements of the constituents into successive ionization states can be expressed like in this way. So combining the Boltzmann and Saha equations in LTE, it is also not linear. This is a non-linear problem, but it is fairly simple non-linear problem. You can devise very simple methods to solve these two simultaneously. This just gives you an. But note that this N has no dependence on the radiation field I. So there is no dependence on the coupling to the radiation field directly. So this is if you have environment where the temperature and electron density are known, you can just couple them. And then
What's the GI?
GI are the statistical weights that account for the region reactions. So yeah. So you have not learned Saha, and this one is actually. But anyway, this is very first and simplified way to compute your populations. If you are given a gas with n elements, then you can use this, and then you will get distribution of elements in different bounded ionized states. However, when LT is not applicable, for example, as I already mentioned, when the scattering becomes important, then actually you have to do what is called as a non-LT statistical equilibrium or the kinetic equilibrium, which is called a kinetic equilibrium equations, where you have to balance the collisional and the radiative rates. The collision, which is called as collisional rate and the radiative rates. So collisional and radiative rates have to be balanced. In this case, the coupling to the radiation field comes into picture. So please remember this J bar term, which is called as a mean intensity. The intensity is integrated over all frequencies and angles, and this is a very important term that drives this non-LTE effect. So again, come back to this picture here. All these processes now become important. And this is the form of the rate equation. So C here corresponds to the collisional rate, R corresponds to the radiative rate, and R here, it actually contains this J bar. And J bar is the integration of the specific intensity over all frequencies and angles, and that I, specific intensity itself, comes from the solution of the radiative transfer equation. So you, as you can see, you assume a source function to start with, solve the radiative transfer equation, you get a formal solution I, and that I you integrate and get J bar, and then put in here, and then you solve this rate system. And the collision rate, basically they depend on temperature and the density of the material, and of course this is an iterative method, so you have to start with what you know in the previous iteration, and then you have to solve. This is like a solving like a matrix problem. So you just solve it, and every grid point it will be an n cross n matrix, where n is the total number of excited and ionized levels. You can use numerical methods such as LU decomposition and all this. So this is the solving the rate system is fairly simple, provided you know the radiation field. But since you don't know what is the proper form of radiation field, you have to devise iterative methods.
So this is a dense matrix or the sparse matrix?
It depends on what you take. So if you take 14 elements and each element having, I don't know how many levels, so it will be the total number of element excited and ionized states of each element you add up. So it is not like millions of things. It depends. Like if you want to include a lot of elements, lot of lines, lot of then it will be huge. It is fairly quick thing compared to the radiative transfer solution itself. This is much. And this is local also. There is no spatial coupling. So at each spatial point, you just invert this and cross matrix. However, the second step is to solve the radiative transfer equation. That is spatial coupling. That is when you have like that is much more complex. And now it can be much more complicated in a dynamical atmosphere. When you see there was the dynamical event like a flare or nanoflare or whatever, then the recombination and the ionization time scales are much more different. For example, there is a shock wave. Then from the multi-simulations, it is found that in the solar atmosphere, for example, hydrogen ionization recombination timescales are 60 seconds within hot shocks, and within cool intershock region, it is very slow. So this imbalance in this, because it quickly ionizes, but then takes forever to recombine. So if there is no equilibrium, it doesn't quickly recombine, then by the time this equilibrium reaches, before that itself, the environment would have changed. So the time scales on which these atomic populations reach their equilibrium with the environment is much more than the evolution time scales of the atmosphere. So therefore, you cannot assume the statistical kinetic equilibrium anymore. But now it becomes even more general, time-dependent, nonlinear radiative transfer problem, where the rate equation on the right left-hand side remains the same. On the right, you have a time derivative of the population, and also you have to take into account perfection. So this is very complex because you have the time dependence also coming into picture in this problem. So now I come to some classic numerical solution of the radiative transfer. Now you have seen how the rate equations are solved, but it's only part of it. So radiative transfer solution is two parts. One is solving the rate system, one actually solving the radiative transfer equation. So the one of the famous like most popular methods is this grid-based methods, non-characteristic, short, this different form in that. So these are some of the grid-based techniques. In particular, the short characteristic Cosmology solution is a popular method in which you discretize your radiation field quantities in each of your computational domain points in the computational domain. And a set of rays are passed through the computational domain, and each ray is divided into the 3 points, say. So you assume that it's like a piecewise adding up your ray into a piecewise continuous function or something, in which each point here, for example, this is an example I can show you. This is your 2D computational domain. All these black dots are the points where you actually compute your radiative transfer equation or any other. If you also have imaged equations, you can solve all these as grid points. So as it is a regulative problem, say in the beginning you know from the previous iteration and source function in all these points. Then the ray, for example, is passing through this point here at 0, you are actually computing the radiation field, and it needs information from nearest neighbors. So it has to know radiation field here and here. Since you don't know this is not falling on any of the grids, you have to do interpolation of the source function and the radiation field using these 3 or 4 points to get information here, and similarly here. And using that, you know source function here, here, and here. So basically, express the source function as a quadratic polynomial using 3 points. Since you know the source function in 3 points, you can express quadratic polynomial. You just substitute that, and then it is an analytical integration. So for a given small polynomial, you can analytically integrate out these things, and then you can obtain this intensity at this point. How did you know this and this? But since these are also depending on the previous point, so and then you trace the way step by step. And eventually, since it is from the previous iteration and so on, you have to do this multiple times. Like you have to iterate it until the final convergence is of time, and then you get a solution, which is convergent up to your limits. And yeah, so basically it uses polynomial approximation for the source function and the analytical integration of the source function at the desired grid point. And there are statistical methods which are called as Monte Carlo techniques. This is fairly stochastic methods. There are different steps. It is a completely different method. Here you discretize the radiation field into photon packets as if they are behaving like a real photon. And initially you have to initialize this radiation field as this, like using random number generation. You have to have a fairly huge circle of this photon depending on your application. And then there are sampling techniques. A set of principles has to be used in order to determine the outcome. For example, whether this packet is absorbed or whether it is scattered. For each of this process, there is a rule. So if this is satisfied, then it is absorbed. If this is satisfied, this is scattered. And eventually, each packet is followed in the computational domain. It is the propagation of this photon until it is absorbed or escaped from the atmosphere. So this is a completely different method. This is also popular in some of the applications. But yeah, it has its own limitations. And then there is other method which is moment formulation of the radiative transfer equation. Basically, in a simple hydrodynamical applications where you just have to know the flux divergence. If the problem is complex, then even we have problems here. But in a simple, relatively simple environment, when you are just interested in the macroscopic quantities such as mean intensity, energy, and mean flux, you use this moments method. But here there is a problem of closure, because normally the number of unknowns is much more than the number of equations. So then one has to use some kind of approximate closure equation. And in some cases it is valid and this works well. But if you want to include more complex physics, this becomes a problem. Now I list some of the codes that are in literature. I mean, there are much more actually, but I have just given a few examples here. This C2 ray, for example, uses short characteristics, which does large simulation of the cosmic reionization, and this the modeling of the H2 region. And this is a general code that can be applied to several cosmological problems to model Lyman alpha Cauchy, reionization, etc. And then for the solar, we have the Radiative code, which does the hydrodynamical solution with non-equilibrium effects, but it is 1D, it cannot take magnetic fields into account. And there are this Bifrost and Muram, and these are the MST codes which are used to simulate the solar atmospheres, but then they have done a lot of approximations in terms of the radiation field. So
including polarization effects is sort of like a standard thing, but they all.
Polarization is not required in the energy transfer. It is if you have an observation, polarized observation, it is like a probe. So if you want to understand, basically polarization comes in two forms. One is when you have a huge magnetic field, then through Zeeman effect, the line splits. And then observation of the Zeeman effect to model these lines, then you have to use the radiative transfer equation to solve. Suppose that you have no atmosphere. So this is like a forward model. You consider different atmospheres. After doing all this complex MHD, then you have finally a simulation box or a 1D atmosphere, using which you can solve radiative transfer equation in all the grid. And then you compute synthetic closeness. So intensity and polarization profiles and compare with the polarized observations. So then you can infer whether this is corresponding to this much magnetic field, or like what is the orientation, what is the map of the magnetic field. This is like a forward model. There is no hydrodynamics involved in that. So because polarization anyway is a redistribution of the energy itself. So here all this thing you do is eventually in terms of energy transfer. So you're giving as a flux divergence to the energy equation. So for the energy transfer, the state of the radiation field itself is not important. So there you do, so hydrodynamics is nothing to do with it. Yeah, so then I am also involved in developing a full radiative transfer code for the chemistry code Mura. We are developing this module, which includes everything like lines, continuum, everything, and also does non-equilibrium and non-equilibrium chemistry. So these are some of the detailed outcomes from the solar chromospheric simulations, which I don't want to go to the details of this. And in particular, we want to interpret the calcium and magnesium lines, which are scattering lines in the solar chromosphere. And this Aditya suit on Aditya is capable of observing this, and one can use simulations to understand this. Yeah, there are multiple applications, and there is also non-equilibrium, time-dependent ionization, and molecular chemistry is also important in non-solar applications. They have non-solar applications in terms of modeling low density primordial gas, upon no atmospheres. Yeah, friends, thank you for attention.
Questions? I think you just compensated the time that we lost in quickly. So
Yeah, it's much quicker.
no, this is actually excellent. So we have time for questions. Just a second.
What is your take on coronal radiation?
It is basically simpler in terms of radiation field. It is much simpler because it is completely mostly ionized there. So the scattering is basically in terms of ion scattering, electron scattering, and all. And the regime is completely different. So, but there the complexity arises from the magnetic field. So the corona is all about magnetic. So radiation is in itself is not that complex. But of course, yes, when you want to do a complete simulation of the solar atmosphere, you have to take energy transfer from the photosphere, chromosphere, and corona also. So then all these things become important. Everything gets coupled eventually. But yeah, depends on the average solar atmosphere. It is like reaching a temperature minimum of say around 3500 Kelvin in the base, like really before it goes up to millions of Kelvin, it goes to a minimum. First it decreases and then it reaches a minimum and then increases. So that's what. So because of the density and temperature scales are so huge, from 1000 kelvins to millions of Kelvin, and the chemistry, when it is cooler, chemistry becomes important. When it is much hotter, then everything is in ionized state, then the different physics comes into picture. So yeah, in that sense, if you are treating completely corona as a different entity, and for some of the problems there, the radiation field and radiative transfer in the coronal layers may not be, but of course it is coupled. So
corona has nothing to do with radiative transfer. It's like I asking her about weather modeling. You can answer it, but the talk is not on weather modeling. Corona is a plasma problem. Reconnection and all these things are important. She's already said that, right?
So I want to know that is there any particular reason that in all the equations of the radiative transfer, so all the mechanisms to explain it, they were all based on electronic models. So you didn't mention anything about thermal radiation and hadronic model radiation. So is there any particular reason why not keep it?
thermal radiation is there. When you say that there is the source is coupled, like there is a thermal source and a non-thermal source. So when the scattering becomes important, I was mostly concentrating on the complex part, which is non-RT. So that then the source function is dominated by the scattering sources. So thermal source is a part which is there, but it is mostly dominated by that. But the thermal, that's what you are saying, that is automatically taken into account through the collisional rates. Basically, you have collisional and radiative processes. The collisional processes automatically take your thermal sources into account. And when the radiation field comes into picture, that couples the radiation field to the
And then what about the hadronic processes? Radiation from the hadronic processes, like
what do you mean?
like PP collisions and like high energy processes.
Oh, that is a complete different scenario that happens in the, of course, you mean PP reactions? This
Yes.
that happens in the core. Like that is a nuclear reaction. That is a completely
I
different.
think he works on cosmic related things, I believe. So that's sort of he's trying to connect it. Again, we're talking highly energetic protons and ions. They are accelerated in the sun by plasma processes. What she talked about was radiation, light, photons. I mean, they are different things. So we can actually talk about it in person, but this is not related. These questions are not related to the talk that she's giving. Okay, it's about the interaction of photons with matters. this is what thought. So are there any questions on radiative transfer and MHD hydro? So what it also says is that you have to know beyond what you do. Otherwise, you will not understand something immediately beyond your expertise. Okay. Anything else on radiative transfer?
Here is one.
Showed that
Wait, later.
sorry,
9:26. I don't have the number here. You can tell me where to stop.
yeah, the next one.
This one?
Next.
This,
Yeah.
yeah.
So there
Is equilibrium or non-equilibrium? Which one you want?
this one here.
Uh-huh.
And here you can use the mind. Intensity is at a point in space, right? It's not throughout the space which you are using, right? Yeah.
You have to discretize your atmosphere into, you are assuming that your atmosphere, say it is like a Cartesian box, or even a simple 1D atmosphere that is like here. For example, this is suppose it is your atmosphere. You have such n points to represent your atmosphere. This is base of the atmosphere. This is top. Like this is from the outside. After that, it escapes. So this is the base, and this is a type of to represent an atmosphere. 1D atmosphere, for example, looks like that, and you have to compute the radiation field at each point like this. So it starts from here, and then it couples to. So, but at every basically, what we do is pass a set of rays. So it has a particular polar angle theta and phi, like you have a particular direction associated with this ray, and then you trace the ray. You start with the bottom of the atmosphere, say. In the bottom, the incident radiation is basically like from the surface of the photosphere, which is like Planck. So that is the initial source at the bottom. And using that source, you can solve the radiative transfer. Once you know the source, you can solve at the bottom.
Yeah.
And then you go back. Yeah. So then each, if you are using short characteristic, you can just use these 3-point stances. And using the known information of the previous point and the source function from the previous iteration, they just go forward. The processes that are there non-linearly in the rate system that will automatically correct for the initial approximation that you reached. So iteratively it will correct. Because
Each next point which you are taking.
did you say?
It will become better with each next point we are taking.
Yeah, but then from in the first iteration, all the number of, but in each point it will be approximate only. Then you have to again do it. So it's like iteration. So you have to do repeatedly until you finally reach a convergence, where convergence means that the solution in this and previous iteration don't have much. The relative error is not greater than some question.
Yeah, I can ask the question. 1D means it's 1D in space, but there are rays going in all directions. Right?
Yes.
So it's actually not just 1D.
Yeah,
We are
1D
used to in
is
hydro.
spatial. Yeah, 1D is spatial.
The rays are all in all directions.
Yes. The 1D means that, so if you have an atmosphere, so when you have a cube, like a 3D cube, the spatial dimensions are finite in all the 3 directions. So when you are assuming 3D, it is finite, 1D, it is finite in the heights, but infinite in x and y. So it is homogeneous in x and y. So that's why there is no the dependence on the intensity or the source function on x, y, z, but only on z. So
Partial by partial x and partial by partial y is 0.
easy.
Anything else? Okay, I think we have that for lunch. Let's thank Anusha for the talk.